Good morning, students. This is the second lecture on Gauss theorem. Now, in the first lecture, we said that it is or it can be used as an alternative method for calculating electric field. Okay, see, it can be used as an alternative procedure for calculating electric field. So that means, suppose if we have a point charge, the Coulomb's law should come from this Gauss law, and also we said that it is based on the inverse square law. So that is based on the inverse square law of electric forces between 2 point charges. That means if we put inverse square law, the Gauss law should come. So in this class, in this lecture, first what we shall do is we shall deduce Coulomb's law from Gauss law and also vice versa. So let's do it. So deduction of Coulomb's law from Gauss law. Okay. So Coulomb's law from Gauss law. Now how shall you do it? Let's take a point charge. So let's make this red because we are taking red as the plus q charge. Suppose this charge is plus q. Okay. Now let's coordinatize this charge. That means we need a coordinate frame, and I want this charge to be at the origin. Suppose these are the coordinate axes. Suppose this is x, this is y, and this is z, and we are interested in the electric field at this point P. At this point P. So first just join this, and this is the r vector, and this charge is located here at the origin. Fine. What we shall do is we will draw a sphere taking this origin as center. So let's draw a sphere. This is the sphere. We take the origin as the center where the charge is located. Now, as far as the symmetry is concerned, which I already discussed in the last class, the field at each point on the surface will be same in magnitude and the direction will be radially outward. So how will the field look like? So field will be radially outward, along this. So this is the direction of the field, this is the direction of the field, this is the direction of the field, this is the direction of the field. It is by symmetry, right? So we can write by symmetry the electric field is radially outwards, radially outward from the surface and its magnitude is same throughout the surface. Okay, its magnitude is same throughout the surface. Now apply Gauss law. Now what is Gauss law? We want to deduce Coulomb's law from Gauss law. So if we take this sphere as the closed surface, this sphere and the closed surface, and all the electric fields are radially outside, so this Gauss law will state that E dot ds for the closed surface S will be the total charge contained within divided by epsilon 0. Now if we take an elemental area on this surface, suppose this is the elemental area, so what will be the direction of this elemental area? Naturally this ds will be always radially outward. So if you take it here, the ds will be in this direction, right? So E and ds, so E and ds are collinear throughout the surface. If you take any point on the surface, it will be the same. It's collinear for all points on the surface, right? So what will be E dot ds? E dot ds will be E ds. So this will imply E ds is equals to q by epsilon 0, which will imply, now E is constant, so E will come out of this integral. This is ds, this is q by epsilon 0, which will imply E times, suppose this distance is r, so now this distance, this radius of this sphere is r, since this is r vector, right? So what will be ds? ds will be 4 pi r square equals to q by epsilon 0. Now this will imply E equals to q by 4 pi epsilon 0 r square. Now since E is radially outward, you can say that E vector is q by 4 pi epsilon 0 r square times r cap. So this is Coulomb's law. Okay, so this is Coulomb's law. So this is the deduction of Coulomb's law from Gauss law. We'll do the vice versa case, that means we'll deduce Gauss law from Coulomb's law. Now we shall deduce Gauss law from Coulomb's law. So let's go to the next frame. Deduction of Gauss law from Coulomb's law. So what shall we do? Very similar. We take a point charge q plus q here, and set up a coordinate system taking this charge as the origin, charge at the origin of coordinates. So this is the coordinate system, this is the origin, this is the origin O. Okay, just a second. This is the origin O and this is the plus q charge. This is the plus q charge. Now take a point P, suppose this is the point P, and join this point P from this origin with a straight line. Right. So this is the position vector r, and these are the coordinates x, y and z. Next step is just draw a sphere taking this charge as center. Fine. Now what is Coulomb's law? At the point P, what is the electric field? So E at this point P, right, if I take it's a vector, it will be 1 by 4 pi epsilon 0 q by r square times r cap. Now if you take an elemental area, or you can take it here as well, the electric field vector will be, the electric field vector will be along this r, okay, and the elemental area vector, ds vector, will be along this. So this is ds vector and this is E vector, E at the point P. Now what is Gauss law? Just write Gauss law. Do not write Gauss law, take the surface integral. Take the surface integral for the closed surface E dot ds for the whole surface. So that is what? That is, just plug in this value of E is 1 by 4 pi epsilon 0 q by r square times r cap. And what is ds? What is ds vector? That is naturally ds times r cap. It will be radially outward. This we have discussed in the last lecture. So ds times r cap. So this will be complete surface integral over S 1 by 4 pi epsilon 0 q by r square ds times r cap dot r cap. Now what is r cap dot r cap? This will be identically 1. So first take the constant out of this integral. 1 by 4 pi epsilon 0 q, and see we are doing the surface integral over the surface, so r is also constant, so take r out, so r square is out, and the surface integral over ds. Now that will be the area of the sphere, surface area of the sphere, that is 4 pi r square. So 1 by 4 pi epsilon 0 q by r square times 4 pi r square. So r square gets cancelled, 4 pi gets cancelled, so the result is q over epsilon 0, right? So which is Gauss law. So the closed surface integral is q over epsilon 0. Fine. Now let's discuss the variation of electric field with distance. Let's take a point charge q. and let's coordinatize it. Let's coordinatize it using Cartesian coordinates. Suppose this is x, this is y, and this is z. Fine. And let's take concentric spheres taking this charge as center. So if you draw a few concentric spheres, how does it look like? Sorry. So draw a few concentric spheres. Suppose this is one. I am drawing concentric spheres taking radius r equals to 1, r equals to 2, then r equals to 3, then r equals to 4, r equals to 5. Now as we go along the radius, let's take any line from the center which is radially outward. At each point you will get the electric field. So how does the electric field look like? Suppose here the radiuses are, sorry, let me write the radius first. So the radiuses are r equals to 1, r equals to 2, r equals to 3, r equals to 4, r equals to 5. Now how does the Coulomb field look like? E is 1 by 4 pi epsilon 0 q by r square times r cap. So we are now interested in the magnitude, so that will be 1 by 4 pi epsilon 0 q by r square, and we know that this is along the radius and it is directed radially outward if the charge is plus q. Fine. Now what will be the field? What will be the field? If you come here, if you come to this point, suppose we plug r equals to 1. So this is E, right? So E for r equals to 1, what will be the field? Q by 4 pi epsilon 0. E for r equals to 2, so that is what? So you place Q by, suppose this is I am referring as E1. So this will be 4 pi epsilon 0 times 1 by 4, and that is naturally E1 over 4. Right, because this is E1, this is E1, right? Now what is E at r equals to 3? So that is Q by 4 pi epsilon 0 1 over 9, that is E1 by 9. So like this the field intensity falls by square of the distance. Right, by square of the distance. So take this intensities as, suppose this one suppose this one is E1. Okay, it's starting from here and reaching here. If this is E1, here at this point it will be 1/4 of this, and here it will be 1 by 9, and it will be all through. If this is E1, this is E4, and this is, that means these will be the electric field vectors when the radius is 3, and here it will be 1/4, and here it will be 1. So if we plot it if we plot it along the radius, this is the radius, how will the electric field look like? It will be an one dimensional plot because E is a function of r only, right? So it will be an, so let's plot it. This is E and this is R. Now suppose this is r equals to 1 and r equals to 1, I said that E is equal to, suppose E is equals to E1, so it will be here. Now for r equals to 2, if we come here, r equals to 2, it will fall by 1/4, right? It will fall by 1/4, so it will be here. It is E1 by 4, that is E2. And for r equals to 3, here it will fall by 1/9, approximately here. So E3 is E1 by 9. This is the point. So these are the points. So the variation will be like this. So the variation will be like this. This is the variation of E. Now, as I have not mentioned this region below r equal to 1. Below r equals to 1, see the r is in the denominator. So as r tends to 0, E blows up and it goes to infinity, and r is always greater than equal to 0. So E will be also greater than equal to 0. E is the magnitude I am talking of. Fine. So this is the variation of electric field for a point charge as we go along the distance. But we must realize, suppose if you have a sphere, of radius capital R, so let's do this. If you have a sphere of radius capital R like this, which is the radius is R and the sphere of radius capital R, and this sphere is a solid sphere. That means it's a ball, right? It's a ball and there is a charge distribution. It is a solid spherical body with uniform charge distribution. Now the question comes, how will the electric field be for this uniform charge distribution? So the charge per unit volume is rho. Now how can you find the field at any point within the sphere and outside the sphere? So we are interested in finding the electric field outside and inside the sphere. Rho is the charge distribution. Rho is the charge distribution, and this is the origin of coordinates. So how shall we do it? Now I give this problem to you. You please try it at home. Then after this we will start discussing in the third lecture. Okay, thank you.